Welcome back, guys. We're going to make some predictions for what our net force versus time, acceleration versus time, and velocity versus time graphs are going to look like for a simulation, and then see how well we do with these. Again, just like we did with forces to start with, when I had you try to connect it to acceleration and velocity because we already knew about those, I'm going to now try to connect the net force with the second law to acceleration and velocity. So the first thing that we need to do is write down the equation for Newton's second law. That's going to be Fnet is equal to ma. What does this mean in words? In words, it means if I have an unbalanced force causes acceleration. So the first thing we're going to do is consider this lazy dog. It has a mass of 25 kilograms. Again, you guys have this in your notes, so you can work along that way as well. It's on a frictionless surface. Predict the graphs for the following situations. I have a net force of 25 newtons on a lazy dog for 5 seconds. Sketch the graph of Fnet versus time, acceleration versus time, and velocity versus time. Not a very good straight line. I'm going to try that again. I want to connect this point and this point in a straight line. That's better. All right, let's check with the simulation. Again, if you remember from our other predictions, when we looked at the girl on the skateboard, someone being pushed along the ground, the people playing tug of wars, we found that net force and acceleration are always in agreement. That means their graphs are going to look the same. And I know that if I have an acceleration of 1, that my velocity should change by 1 every second. So I made this linear. I'm going to pull up the simulation. I'm going to put applied force of 25 in. And I'm going to press go for 5 seconds. Oh, I got to get rid of friction. Friction off. So lazy dog on ice. Applied force of 25. Press go. You see that nice straight line, barely lagging because there's not many people in the building right now. And that's about 5 seconds. So that agrees with what I wrote down. And I'm going to clear everything and go back to the notes. All right, now I'm going to give it friction. I'm going to give it 20 newtons of friction. And I'm going to apply a force of 100 now on the lazy dog for 5 seconds, sketch the graph of Fnet versus time, acceleration versus time, and velocity versus time. So I'm going to give you guys a second to do that. So again, I have a net force. It's going to be less than all of 100 because friction is going to work against me. So my acceleration needs to be a straight line. These two have to agree. And this one tells me how the velocity is going to change. So if I'm starting from rest, I'm going to go up at a straight line. Let's look at the simulation. I hope that the friction hasn't changed, but sometimes. And I'm starting. They're saying the friction is 24, not 20, but pretty close. Velocity is going up. Make it so the graph can be seen. And we'll stop right there. It's about 5 seconds. So they must have changed the value for the coefficient of friction for the dog from last year. All right. Moving on. All right, so now I'm going to take my lazy dog to the moon. And so my acceleration is going to be different, but the mass is going to be the same. I'm going to apply the same force for 100 newtons for 5 seconds, and I want to know what the sketch of the force versus time, acceleration versus time, and velocity versus time. So how does acceleration due to gravity, how is that affected by, or how does that affect the second law? It turns out that it doesn't. So we still have the same net force. We still have the same mass. So that means that the acceleration is just going to be that net force divided by the mass. In this case, that's 100 newtons divided by 25 kilograms, or 4 meters per second squared. And if I'm going for 5 seconds, that means that every second, my velocity is changing by 4. It's going to go from 4 to 8 to 12 to 16 to 20 by the end. All right, so we're going to get rid of friction. I need more controls because I need to go to the moon. So I'll put that in. And I'm going to clear this, say yes. I'm going to make my velocity so I can see it. I'm going to put an applied force of 100, and I'm going to go. So now my acceleration is 4. I'm getting 2 horizontal lines for the force and the acceleration, and the velocity is still only the force divided by the mass. And I let it go a little bit more, but I got to about 20 after 5 seconds. So that would be a common misconception. People would think that if you were to kick a bowling ball on the earth, it would be less painful to kick it on the moon. But that wouldn't be the case. It would be just as painful because it's still the same amount of mass you're trying to accelerate with your foot. All right, now I'm going to go to Jupiter and do the same thing. So if I take my gravity and divide it by 6, I got no change. What if I take my gravity and multiply it by almost 2.5? Is that going to change what my force, acceleration, and velocity are? And I'm going to say no. That was supposed to be a straight line. You guys probably have a ruler at home, so you'll be able to do it a little bit better. All right, let's look at the simulation and see if we're correct. So now I'm going to maximize this. I'm going to change my gravity. Oh, there's Jupiter. Just take it to Jupiter. Get it as close as I can. I'm going to make sure friction is off. I'm going to apply a force of 100, and I'm going to press go. And we're getting the same exact graph as we got on the moon. So it made it up to 20 meters per second. Same acceleration. All right, so the question is, what factors affect this second law? The only thing that affects this is the net force you have and the mass you're trying to accelerate. Nothing else. What does a constant velocity look like on a force versus time graph? Well, constant velocity means that I have an acceleration equal to zero, or cero if you're in Spanish class. So what does this look like? Well, if my acceleration is zero, my force is zero, and it should just be a horizontal line.